Greetings, welcome to the lab on comparing many means using a technique called ANOVA, which is actually an acronym for analysis of variance. So ANOVA is a rather interesting technique. It's used when you're trying to compare many means with each other. It is also a more advanced technique. So we're going to focus primarily not on actually doing the calculations to conduct an ANOVA test. We're going to primarily concern ourselves with how to state the null and alternate hypotheses, then how to interpret the work done by others or like in a journal or something like that to make sense of somebody had done an ANOVA, okay? So that's our goal here. So let's go take a look at slide 2. Let's talk a little bit more about what it actually is all about. So ANOVA is used to assess whether the means of an outcome variable is different from different levels of a categorical variable. What that means is that you have multiple means, you have multiple populations, and what you're trying to do is decide across those multiple populations, those being your categories, are the means for each of those categories the same? Where mu1 is equal to mu2 is equal to mu3 up to mu sub k, where you've got k categories within, k for category because mathematicians can't spell very well, okay? So that's the basic idea of what we're talking about. So the null says there's no difference among these populations with respect to their means. The alternate says that at least one of the mean differs from the others. And so that is pretty hard-boiled. I mean, it's you don't get to change the alternate. It's kind of nice. There's no less than, greater than, or not equals to. It is always the same for ANOVA. One of them is different from the other ones. Okay, so that's pretty much nice because the null and the alternate, more or less in ANOVA analysis, write themselves. The null is the means are the same, the alternate, at least one of them differs. So, when can you use ANOVA? Well, you got to be kind of careful with this test, which is part of why this is a more advanced topic. It takes a bit of analysis up front to decide whether or not ANOVA is the appropriate tool to be using to analyze these hypotheses. So the observations should be independent within and between the groups. In other words, there's no way of knowing what the next event is going to be based upon what the previous one is. In other words, there's no correlation between the groups or within each one of them. If the data is simple random sample, which is our gold standard, and less than 10% of the population is been sampled, then of course that condition is going to be satisfied with respect to within groups. You're going to carefully consider whether the data may be independent. In other words, no pairing. So that's between groups. Make sure you've got no pairing going on. Always important, but sometimes difficult to check. Okay. The observations within each group should be nearly normal, and that's relatively straightforward to check because we know how to do that. We can look at a histogram or a normal quantile plot and determine for normality. Okay. That, again, as when we've worked with means in the past, can be relaxed when the sample sizes are large. If the sample sizes are small, then you really do need to make sure you've got normality within each one of your groups. The variability across the groups should be about equal. That is, the variance or the standard deviation for each category, for each group, needs to be about the same. This is especially important when the sample size differ between groups. So many times statisticians will strive to have what they call a balanced design and see if at all possible, and they know they're going to be using the ANOVA technique to make sure that they have same size samples for each group. And so how would you check this condition? How would you see whether or not the variability can be assumed to be the same across each of the groups? Well, for us, the simplest way that we're going to be able to do that is to take a look at side-by-side comparative box plots and see whether or not there's grossly different variations between groups. If one of them has a massive number of outliers and the other ones don't, or one's got a huge interquartile range and the other ones have small interquartile ranges, then we may want to move on to a different technique than ANOVA, okay? So those conditions at our stage of the game still pretty straightforward. We can check those. So why not do just a 0 t-test? Why not just do a bunch of, grab mu1 and mu2 and then mu1 and mu3 and mu1 and mu4, etc. Why don't we just do it that way? It turns out it doesn't work. There is if you read forward in the book, I'm not going to cover that material here. There is a way of doing that once you've done ANOVA, but you don't do that up front. It actually increases the chances of making a type 1 error dramatically if you do that. So you never do that pairwise comparison as your first go. So, but if you only have two means, then there's no reason to use ANOVA. As a matter of fact, you shouldn't use ANOVA. You use either the C or the t-test. And if we've seen that basically we always use the t-test. So, which is nice. Again, that's kind of hardwired. Out there in the real world, comparing two means, you're always going to see the t-test used. So if you're comparing more than two means, and to see how far apart those differences from each other, if those differences cannot be attributed to just sampling variability, then we will use ANOVA. So what is the basis for the ANOVA test? I mean, how do we actually do it? Well, the ANOVA test works slightly different than the t-test did. In the t-test, we looked at the difference in the sample means, we subtracted from that the different hypothesized means, and we divided that by the standard error of the observation. Well, in the ANOVA test, what you're doing is you're going to compare a ratio. You're going to create a new test statistic. It's called the F test statistic. It's actually named for Ronald Fisher, the great god of statistics. If you have a moment, you ought to look that guy up. Ronnie Fisher is, we all bow to his greatness. Without him, statistics doesn't exist in its current form, and a lot of things in our world doesn't exist, okay? So anyway, large test statistics, again, large values of the test statistic, as with the t-test, will lead to small p-values and cause us to reject the null hypotheses, where small values of the test statistic will cause us to fail to reject the null hypotheses, okay? If the p-value is small enough, the HO is rejected, and we conclude the population means are not equal. So how is the F statistic computed? Well, there are two variabilities that you're going to calculate. You're going to calculate, first off, what is referred to as the variability. Oops, my bad, excuse me, didn't mean to put that in there. We're going to calculate the variability between groups. And the variability between groups, what that means is, remember we had like K categories before. And so this variability right here is an estimate of the variance. We're not using standard deviations here, we're using variance. The variance between each of your K categories. And then the denominator is a second number, and that is a pooled number. And that's the pooled variance among within all the groups. In other words, you give each of the variables standard deviation or variance to your F statistic here, and what it's going to do is basically average those variances and come up with a single number that is the variance for the denominators. The calculatory details for the F statistic are relatively cumbersome, and we're not going to get into those in this class. If you take a second semester statistics or a more advanced stats class, you'll see more about the calculatory parts of it. For now, we'll just say let R2 take the hit, okay? Now, a little bit about the F distribution, or the F statistic, and the corresponding p-value. So the F distribution is a skewed right distribution. And what that means is that it always has a long tail going off to the right, and the majority of the mass will be over here on the left. In an ANOVA test, we always calculate a right tail test. In other words, our p-value is always going to be calculated based upon, there'll be some sort of F observed value. So there'll be some observed value. This value right here is your observed F statistic. And then based upon that, you calculate the area to the right of that observed point. And this area right here, that will always be your p-value. Now again, the textbook gives you the details of how to do that by hand, by either using a table or by using R. But we're not going to do that. We're going to just work a couple of problems and get out of here on this material. The main idea is that you understand where that's coming from, and that, you know, if you were to see this graph with the corresponding p-value, you'd understand that that's what it meant. Okay. All right. So conclusion: if the p-value is small, that means this is less than alpha, we reject the null hypothesis. Oh my lord, so nice, just like before. In other words, that part has not changed. So p-value small, reject HO. The data provide convincing evidence that at least one of the means is difference. P-value large, fail to reject HO. Oh, so kind. So it's really nice in that every test of hypotheses that you conduct in statistics has that exact same structure to it. You base your conclusion on your p-value. Small p-values lead to rejecting the null hypothesis. Large p-values lead to failing to reject the null hypotheses. Okay? All right, so let's go take a look at an exercise. Let's see if we can actually look at exercise 5.41. 1 and see if we can take some of this to work. Okay, so this is the diagram from the page, but I'm going to go over to RStudio real quick because that's where I've got the problem written up, and then we'll come back to this. So GPA and major. Undergraduate students taking an introductory statistics course at Duke University conducted a survey about GPA and major. The side-by-side box plots show the distribution of GPA among the three majors. Also provided is the ANOVA output. In other words, they went in and input the data into R, had R kick out the ANOVA table for you, and they reproduced the ANOVA table for you there. So they want us to write, first off, the hypotheses for testing for a difference between majors and their GPA. Okay, so let's go back for just a second to the slide so we get to look at the different majors we had going here. And notice we had arts and humanities, natural sciences, and social sciences. So those were our three majors. So they already ran the test, so they obviously did the preliminary checking of assumptions for us, but let's run through that real quick. So one of the things that we stated when we were talking about one of the things that needs to happen with respect to being able to run an ANOVA is that the sample variances need to be all approximately the same. And what we see is that these distances right here, which are for each of our box plots, our interquartile range, those are excellent measurements of the variability within each of the distributions, and we see that they're all approximately equal. So since all the interquartile ranges are approximately equal, then check, we've got that the sample variances between groups appears to be roughly the same. Within each group, we're supposed to have that the distribution is approximately normally distributed. As we'll see in a few minutes, is we can calculate the sample size based upon these two numbers. We'll talk about how the Fstatistic has 2 degrees of freedom associated with it, one between groups, one within, and how these two numbers will add up to the sample size. And so it's a rather large sample in a sense, so we're good to go with that. Okay, so let's leave that at that, and let's go ahead and go back to the problem. So let's go back to RStudio here, and let's go write out our null and our alternate hypotheses. So our null hypotheses is going to be mu1 equals mu2 equals mu3. Now, if you want, you can get a little more descriptive than that. You could put in social sciences, natural sciences, etc. for the subscript. Up to you, but just, you know, boilerplate is mu, and there's 3 means, is that the 3 means are equal to each other. Okay, what about the alternate hypotheses? At least one differs. We don't need to have that in our script. In fact, I don't want that in LaTeX. So at least one, not one, but one mean differs. Could be more. Maybe they all differ from each other, but at least one of the means differs from each other. Okay, so that's the null and the alternate hypotheses. And like I said, really sweet in the ANOVA process is that, you know, sometimes we get a bit twisted around in the 2-sample t-test or even a 1-sample t-test is trying to decide what the null and the alternate hypotheses are. Where ANOVA, it's pretty much boilerplate. Okay, so what are the conclusions of this test? So let's go back to the picture here on the whiteboard, and let's see if we can figure out the conclusion of the test. Well, we're in luck. Okay, we have for us the 2 numbers that we need to be able to tell you the conclusion of the test. We were given the F value and we were given the P value. So this is, they call it PR, but this is the P value right here. Okay, so the P value and the Fstatistic help us to determine our conclusion for our ANOVA test here. So our decision, if you think about this in terms of the way we've been doing it, this is basically step 4 in the algorithm of steps that we've been using for doing a hypothesis test, and we see that we would fail to reject the null hypotheses. And the reason we're going to fail to reject is because we have a really large p-value. And that is, we see that the p-value is greater than any reasonable alpha, but we typically would set alpha to 5%, even though it was not stated anywhere. That's pretty much means that the p-value is going to be compared to 5%. Okay, so our p-value here is 0.8068 0.8 and alpha is 0.05. So you can see there's not much evidence to reject them. And if you take a look at our side-by-side comparative box plots, that also looks very reasonable. Let me erase this IQR. It's kind of my way here. Why? Well, because remember that in roughly symmetric distributions, we can use the medians as good estimates of the mean, right? Because the mean and the median are about the same in a symmetric distribution. And notice that all of our medians fall right about the same place. So it makes real good sense that those GPAs are all basically right around 3.6 for each of these three categories for these different majors that the students are majoring in. Okay, so let's go to a blank window for just a minute. Let's talk a little bit about degrees of freedom with the Fstatistic. So the Fstat has 2 degrees of freedom. It has degrees of freedom between and it has degrees of freedom within. So it has degrees of freedom with the text calls groups, okay? And groups, that's the between. I learned it as between, so I'll tend to say between. And so our degrees of freedom groups, that's going to be the number of categories minus 1. And the degrees freedom within, that's going to be the total sample size, which in our case is n, and then it's going to be n minus k, the number of groups that you have, okay? So now if you take these and just add these together, in other words, if I take the degrees of freedom group and I add to that the degrees of freedom within, and again, add here, that's going to be what? Well, k minus k, that's going to go away. Oh, that's going to be equal to n minus 1, isn't it, right? Look, add up k minus 1 plus n minus k, and you end up with n minus 1. So what that tells me is that if I take the degrees of freedom of the groups and add to that the degrees of freedom within, and add one more to that, I'll get back n, which is my sample size. Okay, so cool beans. Why? Well, because we need this to answer the last question. That's why, because back here at the ranch, they say, how many students answered the questions on this survey? In other words, what is the sample size? Okay. Oh, wait a minute, we forgot to fill in our last part, so let's go ahead and do that up here. We failed to reject the null. There is no evidence to infer a difference in mean GPA. Okay, whoop, not GPS, GPA. Okay. All right, so last but not least, what was the sample size here? Okay, so let's go back for a second to our glorious slide here that gave us the numbers, and we noticed that there were 3 groups, and there was what? Our residuals, which is, that turns out to be the degrees of freedom within, so 195 plus 2 is 197. But so if I take those 2 degrees of freedom, add them together, I get 197, add one more to it, and I'm going to get 198. Okay, so the degrees, what is it? It's going to be the DF between, let's just call it DF1, plus DF2 plus 1, which in our case means it's going to be 2 plus 197. Oops, it's not 197. Let me go back there and check it real quick. I think the answer is stuck in my head. 195, yes, excuse me. 195 plus 195 plus 1, which is equal to 198. Okay, cool. All right, well, that is it for our work as far as the videos go with ANOVA. Be sure and read the section. There is a lot to learn about this particular topic. If you go on in statistics, you will definitely see ANOVA again in far greater detail.